This is an ideal vapor compression cycle problem involving R12. Let's switch it to R134, a more common refrigerant. The two pressures of the cycles are given. One is 0.15 MPa and the high pressure is 1 MPa, which means at state 1 the pressure is 0.15 MPa and at state 2 the pressure is raised to 1 MPa. If we draw the TS diagram, this is the lower pressure. So state 1 is saturated by definition in an ideal vapor compression cycle, and isentropically we raise the pressure to state 2. From 2 to 3 heat is transferred out, and 3 is again saturated liquid, and 3 to 4 isenthalpic expansion in the expansion valve reaching 4. What we are after is Q dot C. This is our Q dot C, how much heat is added on the evaporator, and this is our W dot C. So the tonnage of the system basically means Q dot C in ton of refrigeration unit, and compressor power, and their ratio is obviously the COP. So let's begin by finding the 4 different states, and we'll do energy analysis of each of the devices. So let's begin with state 1. First, let's list what we know. Pressure is given 0.15 MPa, and it's a saturated vapor, so X equals 1. So how do you find any property of a saturated fluid? That's very simple. H must be Hg at 0.15 MPa. So we go to the saturation table of R134A PC model. R134 is here. There is no pressure saturation table here, just temperature saturation table. So we look for 0.15 MPa. It's close to, in between these two, so it's closer to, okay, somewhere in between the two. So we are looking for enthalpy. So between 236 and 237. So let's say it's 236 point, let's call it 237. How about that? So we just write down 237 is our answer. And we might need entropy also. So at 0.015 MPa, entropy is somewhere between these two. How about 0.93? Pretty approximate, eyeballing. So entropy is 0.93. So let's go to state 2 now. What do we know about state 2? The pressure is 1 MPa and entropy is about the same because isentropic. So at 1 MPa, we first have to figure out where the state is. Is it superheated or a mixture or what? Of course, you understand from the diagram itself that if this is state 1, state 2 must be superheated. But you can prove it just to make sure. Find out the saturated vapor S. So if we find SF at 1 MPa, and compare that to this, then we'll know for sure superheated vapor. So this is a good practice. It may take a little time. At 1 MPa, we want to find the saturated Sg at 1 MPa. So this is 1 MPa, very close to 1 MPa, and you can see the value is about 0.904 or something, 9045. So therefore, you can see that S is greater than it's Sg. So therefore, it is superheated vapor. So since it's superheated vapor, we can go and find the enthalpy by going to the superheated vapor table, knowing that S is 0.93 and pressure is 1 MPa. So we open the superheated table for our 134A and go to 1 MPa Where is the 1 MPa table? Right here. And entropy is 0.93 in between these two, closer to the second line. So enthalpy will be closer to these lines. So it's let's pick 278, 268 and 280. So you pick a number close to 280, which is 278. So we go and substitute that value here. And therefore, state 2 is now completely calculated. All that is left is state. Oh, there are two more states left. So let's go and calculate state 3 now. State 3 is simple, straightforward, because we know it is saturated liquid. So the pressure is the same, 1 MPa, and quality would be 0. So it's quite straightforward. We go to the saturation table this time again and try to locate 1 MPa line, and 1 MPa somewhere between these two lines, as you can see, 1 MPa. So H enthalpy becomes about 268, almost 268. And finally, state 4, we know enthalpy remains constant, so pressure is known, same as P1, which is 0.15 MPa, and enthalpy is 268. So we don't need to do anything, already enthalpy is known. All that remains now is to analyze our devices. Let me join this just for the sake of completeness here. So let's analyze the compressor first. Well, the compressor power is m dot h1 minus h2, and if we substitute the values, wait, no, it's h2 minus h1, sorry, compressor power is positive, it should be 2 minus 1, and now if we substitute the values, you can see that will be about 1.58 kilowatt. We already found m dot h2 h1. To find q dot c is m dot h4 minus h1. Again, when you substitute the values, you can show that q dot c is 5.28 kilowatt. Then if you divide that by 3.57, then we get in ton, which will be in ton of refrigeration, that turns out to be 1.5 ton of this 3.57 is just a conversion factor between ton and kilowatt. So therefore COP of the refrigeration system, which is Q dot C by W dot C, turns out to be 3.33.